Hey guys, welcome back to week 12. Okay, we're getting close to the finish line. Let's take a look at what they're looking for here. Okay, so I'm kind of gravitating towards C, so I'm going to do that one first. We have this side's equal to this side, so the big triangle here has to be isosceles, meaning their base angles are equal. Now I also know that they share, I see two smaller triangles, and they share that side. So it's evident to me that this triangle here is congruent to this triangle here because of HL, or I could also say angle, angle, side, a couple of reasons. So because of that, using CP/CTC, now that I know that these triangles are congruent, and now that I totally misspelled CP/CTC, then I can set these equal to each other. CD has to equal BD. So let's set these equal and solve. So, no, that one's no good. Let's plug in 2 and double check our answers. So here we get 8 times 2 plus 4. That's 16 plus 4 makes 20. CD is 20. We like it. Let's plug this in. 2, so 4 times 2 plus 12. That's 8 plus 12 is 20. They are equal. So would CA equal BI? Yes, that's shown in the picture by these hash marks. Would CB, the whole thing equal 42? No, that's going to be 40, right? Because this is 20 and that's 20. So the whole thing's 40. Would CAD, this angle, be equal to ABD? No, those are not corresponding angles. This angle would match that angle. That's the angle that corresponds. This angle matches that angle. All right, that was kind of a good, interesting warm-up. Now let's take a look at question 1. Determine the exact area of this triangle. Okay, I'll do my best. So if I had a triangle here, to find the area of a triangle is 1/2 base times height, or altitude. And it's nice if it's a right triangle, which this one is. I just need to know this length and that length, and I can multiply them and then divide by 2. So let's take a look at the information provided. BD is 5, ED, or the whole thing, is 11. So that means this must be 6, because 5 and 6 is 11. AD is 10, so AD is 10. CE is 4. CE is 4. So if I notice something here, this is a right triangle. So I can solve for that side. And that side, I can solve for that side. I'm going to call this X, and maybe I'll call this Y. Okay, so I can solve for, this is going to take me forever. Maybe I'm missing a shortcut here. No, I don't really see a shortcut. Okay. All right, this orange triangle, I have a squared plus b squared is c squared, right? A is 4. B, I don't know. I called X because I just still don't know. And the hypotenuse is 6. So X squared is 20, or X is the square root of 20. So this is the square root of 20, okay? Now I'm going to solve for Y. That's also a triangle. So notice that's totally a right triangle as well, and you know 2 or 3 sides. So you can use Pythagorean Theorem. So A, I'm going to call the small side, 5 squared, right? B, I guess I'm going to call y squared. It's another leg I don't know. And C is the hypotenuse. I'm going to call that 10. So that's 25 and 100. So y squared is 75. Now that'd be too long, but again, I want y, so I'm going to take the square root of 75. So to find the area, though, I need this blue part. Ugh, I warned you. I'm like, I know how to do this, but it takes too long. Maybe I'm missing a shortcut. All right, so now the yellow one, I know 2 of the 3 sides as well. So I'm going to solve for this. I'll call that z, my last side. So my short leg is the square root of 20, and I'm going to square that. My medium side is z, so I'm going to square that. And my hypotenuse is the square root of 75, so I'm going to square that. So what do I get? Well, interestingly, when you take the square root of 20 squared, you just get 20. And same thing, square root of 75 squared is just plain old 75. So if I subtract 20 on both sides, what do I get? 40, 50, 55. All right, so z would be the square root of 55. So I have my answer, the square root of 55. Now I can plug in my formula. So the area is 1/2 the base. So it looks like the base is the square root of 55. And the height is the square root of 20. So the square root of 55 times the square root of 20. That's the same thing as just square rooting 55 times 20. So 1/2 times the square root of 110. That's the same thing as saying, you could turn that into a decimal too, but that's the same thing as 11 times 100, right? And the square root of 100 is 10 times 10 is 100, right? So this would be 10 divided by 2 times the square root of 11. So 5 times the square root of 11. Whew. That's crazy. I don't think they'd pick that. Let's move to another one. Maybe, like I said, maybe I'm missing something. So it says, given the measure of angle BAD, this one is 3x plus 4. And then also given CAD, this one is 5x minus 10. Find the exact measurement of BAC. Okay, that is BAC, the whole thing. So if I know the blue one and I know the red one, I can add them together. Now, are they the same? I put one arc mark, but that was a little dangerous. I should figure out if they're the same. But if I look at my evidence, they both share a right angle, they both share a side, and they both share this side in the middle. And so that is hypotenuse leg. So because of HL, I can say that triangle ABC is congruent to triangle ACD. And because of that, this angle here at A has to match that angle here at A. They're in the same position. So I can set these equal to each other to solve. All right. And divided by 2. X is 7. So I can plug this back in and check my work, right? 3 times 7 plus 4. 21 plus 4 makes 25. Let's try this one. 5 times 7 minus 10. So 35 minus 10 is 25. Beautiful. So if this is 25 and that is 25, what is the whole thing? The whole thing has to be them added together, or 50 degrees. Nice work. Question number 4. What is the value of BF? Ooh, we did a couple of these in class. These are kind of cool. Okay, so that's 8 and that's 8. Notice they share this side. So that's hypotenuse leg, okay? That means this length and this length must be equal to each other. F is the midpoint. What else do we see? Well, we notice this is 25, right? And this is 25. So it's an isosceles triangle there. So that must mean these two base angles are equal, and I'm not planting evidence. They have to be equal. We also know that this side is shared. So that tells us that this angle on top, this triangle here, excuse me, is a direct replica of that one because of HL. So that means all their pieces and parts are congruent. Okay, so what does that mean? Well, that means if this is 2 times the square root of 39, then this is also 2 times the square root of 39 because that's a midpoint. So it means this one must be 1 square root of 39, and this one must be also the square root of 39. And so if we add them together, the whole thing AC is 2 times the square root of 39. So what is one of the distances? What is BF? I don't know. We haven't figured that out yet. Oh, I spoke too soon. Okay, now I have to identify this triangle. So zooming in on this triangle right here, I know that this leg is BF. This is the one I'm looking for, right? BF, I don't know. I'm going to call that X. This hypotenuse is 8. This is the square root of 39. So I can solve for X using Pythagorean Theorem. Right? So I can call this A, the square root of 39 squared, right? This B, X squared. And the hypotenuse is 8, so 8 squared. Now, interesting, the square root of 39 squared is just regular old 39. You undid what somebody else did. So there, those are inverse operations. 8 times 8 is 64. Now canceling that, we'd get, what is that, 25? Ooh, nice. So the square roots of 25 is 5. That's a sneaky one too. They're really giving us some curveballs. Okay, let's look on the back. Find the center coordinates of the oh, my favorite, circumscribed. Meaning our circle fits on the outside, right? So something like that. So all my children always bring in peanut butter cookies. So angle bisectors make incenters. Perpendicular bisectors make circumcenters. Right, so let's see. Chop 4 in half, bam, line it up. Chop 6 in half, bam, line it at a 90, line it up. Chop this one in half at a 90, line it up. So I'm all converging on this point. Oh, this is all of my children. Something like that. Yeah, so find the coordinates of the circumscribed circle. I'm getting the coordinate 2, 3. There it is. Okay. 6. What about an inscribed? Well, that one's a circle fits inside. So what does that mean? Well, this is a radius and this is a radius, right? So QP, we have an expression for, and RP we have an expression for, and all radii are equal. So they're equal of the same circle. So we should be able to set QP equal to RP. So QP, RP. Distribute, copy back down. Get x on one side. And get x by itself. X is 3/2. Okay. Now, is that what they looked for? They said nope. They said the radius. So I just need to plug this back in. So either one would work. So I'm going to use RP because it's a little sort of. RP is equal to 3 times x, but we know x is 3/2. So the radius must be 9/2. Or you could fill it in as a decimal. That's 4.5. Nice. Question number 7. Knowing that NJ, so let's jot that down. NJ is 10 inches. Okay. Okie dokie. Find the length of PJ. So it looks a little bit longer, doesn't it? Okay, so I'm trying to find the length of this, and I can't use x because there's already an x there. So I'm just going to call that y. All right, so let's do a little digging. It looks like they were all made by angle bisectors. See how each angle was bisected? So angle bisectors always bring in. They make in-centers. And in-centers have an egg, a little circle that fits inside. You see how that fits inside? And the little circle has 3 equal radii, and all radii of this same circle must be equal. So if I take a look here, and here, it's going to be x is 6, but I don't need 6. I need to know the length of PJ. Okay, so at least though I can solve for this PN. So what is PN? It's whatever the length of any of these radii. So now that I know this is 6, 6 times 6 minus 14. 36, take away 14. That would be 22. So this is 22. This one should also be 22. So if 3 times 6 is 18. Plus another 4 is also 22. So we know this one's 22. And now we can use Pythagorean Theorem to solve for y. Okay, so I can solve for my hypotenuse. I just do a squared plus b squared is my hypotenuse squared. So I usually make my smaller side 22, but it doesn't feel smaller. So my picture's not really to scale. My other side was 10. And my hypotenuse is what I'm solving for. So, I need a calculator. I mean, I don't need one. I can do that by hand, but then we'll move a little faster. And that's 100. So what is y? It'd be the square root of 584. And I'm okay leaving my answer just like that, at least for now. Didn't say to make it a decimal or anything. Okay. In ABC, segment CJ is 15. So A, B, C. So in this figure, this length, CJ, okay, CJ is 15. Is it necessarily correct that KJ has to be 5? Does this have to be 5? Interesting. So the answer would be yes if those were I'm forgetting the word right now. And again, I'm looking over here like, what's the word? I took just regular bisectors. And this is, cut that in half, go through there. If G is cut in half, that would go through there. So that would be a third of that if I had at least one other line. So it looks like not necessarily. It doesn't look like G, so I'm going to say no, not necessarily. I need at least one other line. I need to make sure G is the midpoint of CB. And right now it doesn't give me that information, so it's kind of not enough information. Okay. So we have our in-center, which is the circle that fits inside. Our circumcenter, which is the circle that fits outside, right? My orthocenter, that's from my altitudes. Boo, right? Boo. Maybe something like that. That's from my altitudes. And then I'm trying to think of the last one. I don't know. I'll have to look up. Let's look it up. So let's see. I'm just completely drawing a blank. It's very late at night. Well, I know. Not super late, but. Types of triangle centers. In-center, orthocenter, circumcenter, centroid. Where was I? Oh, I found it. I found it right down there. Okay. Yeah, and that's our balance point, and that's this one. So I can't confirm. Without that, I can't confirm that point K is my centroid. So these are called my medians. So this is altitudes make orthocenters, medians make centroids. Yes. Altitudes make orthocenters. That's where all that comes from. Okay, let's look at 9. Consider ABC, let M be the centroid. M is the centroid. What is AM rounded to the nearest tenth? So the centroid. So what does that mean? Well, that means I cut it in half and swim to the opposite side. I do it again. I cut it in half and I swim to that opposite vertex, right? You see that I cut that in half? So I found the midpoint, but I don't want to call it M because I guess they want me to call something else M. So I'm going to call this D, E, and I got to find the middle of that. That looks about right. And go to the swim to the other side. So this is my midpoint. Now remember I have some really cool ratios. It says, what is AM rounded to the nearest tenth? AM, all right, whatever the whole thing is, like let's say if the whole thing was 6, then 1, 2, this would be 2, 4, 6. Then this part would be 4, and this part would be 2, and the whole thing is 6. Now let's look. How long is the whole thing? So let's just kind of approximate here. If I made this a right triangle, so that would be the hypotenuse of my right triangle. This is 4, so I could do a squared is 4, right? And this is 4. B squared is 4. And the length I need, my whole length of my median is, I don't know, right? 16 plus 16 is C squared, so 32 squared. Ooh, so, but I got to take my square root. So C is equal to the square root of 32. Okay, so let's find the decimal of that. And then I need, the length they're looking for is 2/3 of that. Okay, so the square root of 32 is 5.656. And I need 2/3 of that. So 2/3 of that nearest tenth, I get 3.8. So it's almost 4, and it was actually close to what I approximated. I thought it would probably be close to 4, because this whole thing looks about 6. See how that whole length looks about 6. Nice. Question number 10. Using the figure in item 9, the orthocenter. So the orthocenter is made by altitudes. The orthocenter for ABC is at point N. What are the coordinates of N? Okay, so I'm going to have to erase this stuff because I need some room to find my orthocenter. So my orthocenter is, boo, splat, right? And I'm going to do it again. Drop an egg. Flip. I'm turning my thing around, but you can't see it. Drop an egg. Boo, splat. I need that to be 90. And last one, I need this to be 90. If this was the surface, I drop an egg out of an airplane, it looks about 90. So I need the extension of all these lines. This should come as no surprise. My orthocenter is somewhere out here. And we know that orthocenters from class, we knew before, orthocenters of obtuse triangles land outside. So let's see what this is. I end up at about +8, -1-ish, positive, maybe -2. Ooh, and there I go. That's my coordinates. So it looks like, let's just clean this up a little bit. It looks like just down a half of one. Let's line that up. That looks pretty accurate, right? That is my orthocenter. Nice work.